In Move, structs are user-defined data structures that contain typed fields of complex data or no data. They can be described as a simple key-value storage where key is a name of property and value is what's stored. They are defined using keyword struct. Struct can have up to 4 abilities. They are specified with type definition. They can store any non-reference type, including other structs. Structs are defined inside a module and have naming restrictions. Struct values can be considered resources if they cannot be copied or dropped, requiring ownership transfer. By default, structs are linear and ephemeral, meaning they cannot be copied, dropped, or stored in global storage. However, these behaviors can be relaxed by granting structs specific abilities. Struct is the only way to create custom type in Move. Let's explore the concepts of structs and resources in Move with some coding examples. To define a struct in Move, you declare it inside a module using the struct keyword. Here's an example. In this code, we define 3 structs, foo, bar, and baz. Foo has 2 fields, x of type U64 and y of type bool. Bar has no fields, and baz has a field foo of type foo. By default, structs are linear and ephemeral. To grant additional abilities to a struct, such as copying or storing in global storage, you can annotate the struct using the has keyword, followed by the desired abilities. Here's an example. In this code, the struct foo is granted the copy and drop abilities, allowing it to be copied and dropped. To create a value of a struct type, you use the struct name followed by the values for each field. Here's an example. In this code, we create a value foo of type foo with x set to 0 and y set to false. Then we create a value baz of type baz with the foo field set to foo. Struct values can be destroyed by pattern matching, where you bind or assign them to patterns. Here are some examples. In this module M, we have 3 structs, foo with fields x of type U64 and y of type bool, bar with a field foo of type foo, and baz with no fields. The module contains 3 functions, demonstrating the destructuring of foo instances. In the example destroy foo function, we create a foo instance named foo with values x as 3 and y false. Using destructuring, we bind the values of x and y to variables x and foo y, respectively. After destructuring, x will be assigned the value of 3, and foo y will be assigned the value false. In the example destroy foo wildcard function, we have the same foo instance. Here, we use a wildcard underscore in the destructuring pattern for the y field, indicating that we don't care about its value. Thus, only the x field is destructured and assigned to the x variable, resulting in x being assigned the value 3. The example destroy foo assignment function demonstrates destructuring in an assignment context. We declare 2 variables, x and y of types U64 and bool, respectively, without initializing them. Then we directly assign the fields of a new foo instance to these variables using the destructuring syntax. The x variable is assigned the value 3, and the y variable is assigned the value false. Note that in this example, we use type inference to determine the types of x and y from the foo instance being destructured. In these examples, we use pattern matching to bind or assign values of structs to specific variables. The fields of the structs are accessible through these variables. You can create references to structs or their fields using the ampersand and ampersand mute operators. Here's an example. In this code, we create a struct foo of type foo. We then create references foo ref, xref, and xref mute to foo and its fields. We can read and modify the fields through these references. To read a field's value, you can use the dot operator. If the field is implicitly copyable, you can directly access it without borrowing. However, if the field contains non-primitive types, you need to use explicit syntax to indicate the copy operation. Here are some examples. In this code, we create a struct foo of type foo. We then create a struct bar of type bar with foo as its field. We can dereference and copy the field foo using the explicit syntax *& bar.foo. However, directly accessing the field without copying bar.foo would result in an error. Structs in Move have ownership semantics, and by default, they are linear and ephemeral. This means they cannot be copied or dropped. If a struct represents a valuable resource, such as money, it should not be copied or destroyed. However, you can grant the struct the copy and drop abilities to enable copying and destruction. Here's an example. In this code, we have a struct foo representing a resource. The functions copying resource, destroying resource 1, and destroying resource 2 demonstrate the restrictions on copying and destroying the resource due to the default linear and ephemeral behavior. To store a struct in global storage, the struct must have the store ability, and all the values stored within it must have the store ability as well. Only structs with the key ability can be directly stored in persistent global storage. We're going to cover ability and global storage deeper in a couple of moments. The example below illustrates how you can use structs and resources in Move. In this example, we define a struct coin representing a coin resource. It has the store ability, allowing it to be stored in global storage. We provide functions for minting new coins, withdrawing coins, depositing coins, and checking if a coin has a value of 0. This example demonstrates how structs and resources can be used in Move to model real-world concepts and manipulate data in a structured manner. Feel free to pause the video here and become familiar with this coin example. Also, always feel free to reach out to me on Twitter if you have any questions.